Hello, everyone. Thank you for joining me. My name is Byung-Yoon, and I work on Gray Lab security team. In this session, I'd like to talk about what kind of a threat line had faced and how we made an infrastructure of live services more safe. Let's start. Let me briefly introduce myself. I'm currently a security engineer at Line. I conduct security risk assessment of services and infrastructure. Before joining Line last year, I'd worked at Grey Hash, conducting offensive research and penetration testing. I used it to penetrate client networks and access sensitive assets. Now, I'm improving Line's defense by using this background and perspective as an attacker. Recently, there have been many security accidents. While most companies value security, there are still intrusion and information leaks. How does the attacker disable a lot of security solutions and infiltrate inside? Let me start with what problems are there from an attacker's view. This is the simplest form of a sample service. Everything is on the internet. We have a web server, an API server, and a database server as a component. The user connects to the web server using a domain name. Then browser may request to API server to communicate. These two servers are basically exposed to the user. But the database doesn't have to be accessed by user. So the IP address or domain name is not disclosed to the user. However, an attacker can scan the same network range to find the IP address of the database. Or the attacker could be able to guess domain names and try to ping them to see if such host exists. That is, when the attacker figures out the IP, they can reach the database server because it's on the public network. To block such access, the database can be access controlled using password. So even if an attacker can access the database over the network, it can restrict access to data inside. Only the API server and web server can access the database using password. Similarly, a developer or an operator may access the database using password and do their job. But is this enough? Maybe no. From an attacker's view, a configuration like this one exposes many problems because it allows anyone to access server to which they do not have to access. Let's find out why. First, an attacker can try to log in using a list of weak passwords. For example, an attacker can take a list like 10,000 most common passwords and try to log in. And can also try combining the numbers and special characters with the list. If the administrator has set it to a bad password, the attacker can log in to the database. It sounds funny, but it works. To find the other attack point, an attacker could scan port open. The attacker may find out SSH port, web page for management and monitoring, or some test page, or debugging page, and so on. All of these are good points of attack for an attacker. For another scenario, an attacker can try to use exploit code. Exploit is a code that attackers take advantage of a vulnerability to do remote code execution or privilege escalation or install malware and so on. If a server OS and software are not updated well, it's easy to gain full access leveraging disclosed exploits. You can find this exploit very easily. For example, if you search Google for Redis 5 exploit, then you can find this attack code. In short, if an attacker can reach a server, the server is exposed to a lot of security threats. So how to defend? Expose only those components that should be accessed by users to the public network and contain the rest inside the private network, like this. Expose only a web server and API server that need to be accessed by users and contain the rest inside the private network. Database, internal API server, for example. And focus on monitoring web server and API servers that are exposed to the public network. If the aforementioned attacks are detected on the web and API server, we can block them. There are far more internal servers than externally exposed servers. So this structure is highly efficient. In this configuration, an external attacker cannot reach the servers in the private network. This blocks all the attack vector I mentioned in previous page. I think it's a little safer now. However, the size of a private network grows as the size and number of services grow. Number of web and API servers exposed to the public network also grows, and security threat along with it. Legacy or unmaintained services occur inevitably. It may be a server that the developer opened to the outside for testing. They provide attackers security holes into the private network. If an attacker penetrates into a web server of a legacy or unmaintained service, attacker will also be able to access other server in private network via the server. For example, the database will be accessible via the server. But the more serious problem is that servers in other services are also reachable. This method attack is called lateral movement attack. In many breach incidents you see in the news, the target service is not directly attacked, but attacked by lateral movement from inside the private network. An attacker first infiltrates into private network through an abandoned or vulnerable server, then pivot to attack critical services infrastructure. Since we focused monitoring on servers that are exposed to the outside, the monitoring and security of internal network is relatively weak. In some cases, people don't care about security of internal network because it's not reachable from the outside. So security that simply rely on the benefit of private network is no longer secure. Now, let's take a look at what's going on with Line. There are many services and there are many servers facing the internet. Similarly, many security solutions protect servers that are exposed to the outside. Moreover, a handful of critical services are inside their own separate private network. Services inside the separate network are safer against lateral movement attack. However, many of the services without dedicated private network are exposed to potential threat of a lateral movement attack. Access between servers inside the private network is allowed for the sake of intricate interoperation. So we wanted to achieve the level of security in which every service is as secure as having its own private network. We also wanted to identify and control connection between servers inside each private subnetwork. For example, one Redis server is open on port 7000, and 10 API servers access and communicate through this port. This Redis server also has infra provisioning agent on port 5000. Infra provisioning server access this port to send management command. So we set the following access control rules for port 7000 and 5000. Port 7000 is accessible only from the API server, and port 5000 is accessible only from the infra provisioning server, and block or other connection. With this structure, port 7000 on Redis cannot be accessed by a server in other services. It's an ideal design, but it's actually very difficult and complex task to implement. For line, there are hundreds of databases in one service and thousands of API servers accessing the database. And the servers that we already have run in physically different places. And it's a very dangerous approach because if a rule goes wrong, it can lead to failure of the service. But if configured well, the service will certainly be safer. This is where our adventure starts. A hardening we are trying to do is to block all unnecessary access at network level. First, we had to find a tool to block access to the network. Before choosing the tool, we first listed the requirements for the tool. First, support multinational and distributed infra. Second, Line has a dedicated infra as a service, so this in-house cloud infra should be supported too. Third, support for pre-existing infra easily. Last, low workload overhead for each maintenance, because security team resource is limited. Major candidates for network access control are IP tables and network firewall and host-based firewall. IP tables is a command on Linux. It's very simple to use. You must have a root privilege to run, and you can execute the command with argument to register rule. Pros of IP tables are developer or operator may configure the rules themselves in extreme situation. It has no cost, and it is host-based, so no physical constraint. Can be used with the cloud infrastructure. Cons of IP tables are developer and operator may make arbitrary change because they can. This can make security holes, and it's very difficult to centrally administer IP tables. It's too much work to add a single rule to hundreds of servers. When a log collection cluster expanded, for example, thousands of servers should be accessed and have the rule applied. Automation is possible, but we assessed that its stability does not meet our expectation. Network firewall is a hardware device to filter traffic between two or more networks. It also acts as a router or switch. This firewall has a separate IP and provides a management web page for registering rules. Because network firewall is a separate hardware device, so it costs no resource overhead for servers. Because Line's already using these firewalls, we have enough experience and know-how. Cons of hardware firewalls are they are costly, especially when we need one firewall for every private network. Moreover, it's a physical device, so it needs physical proximity. But servers are usually scattered across a huge data center, and cloud instances don't even have a physical presence, so no go. Let me explain host-based firewall briefly. Host-based firewalls run on host computers and control network traffic in and out of those machines. You set up host-based firewall as follows. First, make the required rules with the management console. Second, install the firewall agent on the host to which you want to apply the rules. The host is then registered in management console. Finally, apply the previous designed rules to desired host. A rule is passed on each host to each host and applied. Host-based firewall may complement shortcomings of IP tables. We discovered that Trend Micro's deep security solution is already in deployment. So we took a look at that. It's a host-based, so merits of IP tables stay the same. It provides central admin console, so maintenance cost scales. And it provides API, so can integrate with our infra management tools. Most importantly, it provides detect-only mode, so it is possible to monitor rule violations before starting to block them. Host-based firewall solution sounds most efficient in many ways, so this is our choice. Hardening followed these steps. First, we analyzed the target service's characteristic. Second, we came up with a process to apply new defense. Then we applied the process. The first target is the database servers for service A. To choose the first target, we looked through the list of more critical services. Then from there, we looked for a service with an adequate level of complexity, because this will be the base case for the other in the future. The service we choose was using various database types, like HBase, Cassandra, Redis, MySQL, and so on. The database servers were about 700 in number, and databases were categorized into 27 groups depending on importance and data type. And the number of clients requesting connection to them were about 2,000 in number. Some database maintained an older version for the sake of compatibility. So hardening this service was also very meaningful from a security perspective. Database servers and the servers that connect to them were all scattered all over the network. So servers in a group is not placed in the same network area. We cannot use CIDR format. It means that we have to create one rule for each client. And because each one of the critical services, we had to apply new defense without causing downtime or failure. Rephrasing, we were required to apply firewall seamlessly with hundreds of servers, dozens of server groups, and their daemons experiencing no stop or restart. This is the prototype design of the application process based on the firewall setup and operation procedure. First, in order to make the rules, we had to collect all the network connection information of the database server. We asked the development team to collect a list of all clients accessing each database. there were API server, or batch server, or monitoring servers. However, database servers did not only use database-related ports. The ports used for infrastructure management and provisioning. These were collected by the infrastructure management team. Based on the information collected, we could create rules that define the IP list to allow per server, per port access. And the second step is, because the way we use the host firewall, we need to install the firewall agent on all hosts we want to protect. The total number of target servers was approximately 700. This task can be installed in batches using the infrastructure management tool. Once the installation is complete, we can build a host on which the agent is installed from the management console. After grouping each host into clusters, we assign the rules that we created earlier to the right host. When a rule is assigned to a host, it blocks unnecessary connections. After finishing the design, we reminded ourselves of challenge again. No service failure and no service downtime. The target we are trying to apply was already running for public use. One minor mistake could lead directly to a failure. So we listed possible problems in every page. In the first page, the developer team may omit or record incorrect info by mistake. The infrastructure team may miss out on some essential infrastructure management traffic. Or I may make an incorrect rule by mistake. These mistakes will result in service failure. In the second page, the agent software may cause system failure because it's a kernel module-based agent, so kernel panning may occur during installation. The software itself may malfunction or conflict with other kernel modules. These problems were likely to make the system unusable. In the last page, although firewall itself is okay, the service performance may be not okay. Adding more rules as you go may also cause unexpected resource overhead and new problems. So we've also looked at the performance material that vendor provide. It's not exactly the same as our service environment in quality or volume. Some unforeseen problem may occur. So these are how we decided to prevent these problems. First, to prevent faulty rules, we use detect-only mode without enforcing control for a week. And log violations. We can evaluate our rules based on the logs. This will allow us to correct any invalid rules without creating a service failure. Second, for unpredictable failures, we first test a single server with a redundancy. Most databases are redundant for the sake of high availability. So this is not a problem even when a single server fails. This is improved process. Every server group operated for a week in a detect-only mode and was monitored to check presence of missing rules. We first applied this to a single server, then did so on the first half of a host, and then on the other half. Application process was conducted on 27 server groups independently. We took 2 weeks to apply the firewall to all server groups sequentially. by 2 or 3 groups per day. This was to secure a resource to respond to failure. Since this was the first application case, we expected to have unexpected problems. To respond to them, Dev and Infra team carefully monitored service metrics and logs. Every time a firewall is installed and rule is applied, a separate communication channel is created to notify any critical events between Dev team, Infra team, and security team. If there was any problem, we stopped and solved the problem and then proceeded to the next step. Through this vigilant process, firewall rules have been safely applied to about 700 hosts, and network-level security of 27 server groups has achieved the security level almost equivalent to that of mutually exclusive 27 private network. And no service failure caused by this hardening task. It's a system. Sometimes after the firewall application, there have been expansion of the service API cluster, that is client of database server. But the servers didn't register to the firewall. So as they were deployed, valid traffic was blocked off by the firewall and resulted in service outage. After health recovery, we came up with a countermeasure. We thought, if it's impossible to prevent human errors, then at least detect it quickly and respond to that. So we built an alert system that notifies dev and security teams when deny events are observed in the logs. The alerts body shows not only source and destination IP address, but also other details like a server group information. This helps grasp the situation quickly. Through the alert system, before the new server was put into service without registering, we were able to detect the missing rules and prevent accidents caused by human error. Speaking in detail, the Scareout is as shown in the figure. The server is allocated and provisioning is performed and deployed. Application run on the desired server group. Then they are assigned to load balancer to handle the request. You may get an alert between this deployment and the assignment. We were able to fix the problem before we put it in the service. This method was able to detect missing rules very effectively. Sometimes after building the alert system, we got a massive amount of the alert of block access. We first figured that it must be a scan. So we got to it right away to investigate a breach. We quickly propagated to every security team information about scan source IP and suspicious findings. To our relief, it was discovered to be a penetration test to simulate an attacker inside our private network. This ended as an episode, but it became a good example because we were the first to detect the scan attempt. New firewall system has been running for a while without causing any outage. But when we thought the hardening adventure was over, we got a comment about inconvenience from a dev team. The inconvenience is, firstly, emergence deployment and extension may be delayed because it required supervision of a security team. Secondly, it's a high maintenance job for both teams to operate firewall with detailed rules. Convenience and security are known to need trade-off, but there must be a way to get very good security while sacrificing very small convenience. So we decided to find out the root cause for the inconvenience. The firewall rules are too complex for developers to fully understand. So whenever a server is added, it's unclear which rules need to change. And it's difficult to see how to change them when the change is necessary. So we are building a firewall control service to address the issues. First, we hide a set of rules irrelevant to developers, only exposing simple rules. We are planning to provide simple UI to modify them. Ultimately, we will link it with a deployment tool so that firewall control system will be aware of any new deployment belonging to a particular deployment group and auto-configure rules to support seamlessly expansion. Let's take a look at the scale-out process we saw earlier. First, you get a new server and provision them for use. In other words, at this time, it is determined which cluster of services this server will be used for. You are usually added to the deployment group for the deployment tool. Line has in-house deployment platform. So if the firewall management service interacts with the deployment group on this platform, when a server is added to a deployment group, you can also create rules automatically on the firewall. This will enable developers to achieve safe network hardening result by doing the same work as before the firewall was applied. It's very convenient. So we are working hard on this task. Finally, the hardening could not have been done by security team alone. We could pull it off only because both dev team and infra team were aware of its importance. It allowed us to cooperate well, which resulted in successful application without outage. So I believe that Line will be more secure because we have the culture that values security. Let me finish my story. Thank you.